This is an example lesson showing how to find the image location and image qualities of a converging lens. That would be a convex lens or one that has a positive focal length. I'll show you how to do it algebraically using the lens equation and also how to draw the ray diagram using principal rays. Now, it turns out there are really only two cases when you have a converging lens, two types of behavior that you can have with a converging lens. One case, which I will do first, is when the object is located further away from the lens than the focal length. So in this particular example, I have chosen a focal length of 2 centimeters and an object distance of 5 centimeters away from the lens. Okay, so let's first do it algebraically. Okay, we'll use the lens equation, which is 1 over the focal length equals 1 over the object distance minus 1 over the image distance. So in this case we have 1 over 2 centimeters equals 1 over 5 centimeters plus 1 over di. Subtracting 1 over 5 centimeters from both sides gives us 1 over 2 centimeters minus 1 over 5 centimeters equals 1 over di. Now we need to find a common denominator between 2 and 5, which of course is 10. So we would have 5 over 10 centimeters from the 1/2 minus 2 over 10 centimeters from the 1/5 equals a 5 minus 2 is 3. So that is 3 over 10 centimeters equals 1 over di. So if I take the reciprocal of both sides, then we get that di is equal to 10 centimeters over 3. Or di is equal to 3.3 repeating centimeters. Because we got a positive image distance, okay, that means that our image is going to be real. Let's find the magnification. Okay, the magnification, M, is given by minus di over do. So that's minus 3.3 centimeters over 5 centimeters, and that is a negative 0.6 repeating, 0.66. The fact that we got a negative magnification means that our image is going to be inverted, or what you would call upside down. Okay. Now, and it will be about 60% as big as the original object. Now, that's how we do it algebraically in the case where D0 is greater than F. All right, now let's do it the same problem geometrically using the ray diagrams. Okay, now you'll want to have a straight edge when you do this because it's important to make sure that your lines are straight And you'll need a ruler because the relative distances are important if you want to get an accurate ray diagram. Okay, so first you draw the principal axis. That is the dashed line. The principal axis is the dashed line that I've drawn right here. Okay, you draw your lens, and then you draw your focal point. Here is one, and here is one. Put it on each side of the lens, and make sure you measure with your ruler so that both focal points are the same distance away from the lens. Okay, once you've drawn the lens, you need to place the object in the correct location. In my example, the focal point is 2 centimeters away, so the object distance needs to be 5 centimeters away. So I'm going to put the ruler down on my screen, okay, and I will put the object 5 centimeters away from the lens, which is right here. There's my object. Okay. Once you have the object and your lens drawn with the principal axis and you've marked your focal length on both sides, then you can, let's see, I'll just mark that with an F and not with an F. You can draw the principal rays. Now, there are lots of rays that are going to pass from the object through the lens. There's an infinite number of them, in fact. But 3 of them are particularly useful for deciding where the image is going to be. So those 3 particularly useful rays are called principal rays, and I've listed them for you up there in the upper right-hand corner. And we'll draw them in that order. Okay, the first principal ray that we will draw is a ray that comes from the object and is parallel to the principal axis, will pass through the lens through the focal point on the other side of the lens. So first, draw a line that starts at the top of your object and is parallel to the principal axis. When it gets to the center of the lens, then it will emerge from the lens through the focal point on the other side, like that. That's principal ray number 1. Principal ray number 2. Rays through the focal point will emerge parallel to the principal axis on the other side. Let's do that. So put your ruler so that your straight edge passes over the top of the object and through the focal point on the same side of the lens. Okay. Oops, my ruler slipped. There we are. When it gets to the middle of the lens, that ray will then emerge parallel on the other side, like that. Okay. Then, finally, principal ray number 3. Principal ray number 3 will pass through the center of the lens, and it will not be deflected. So, put your straight edge, put one part of your straight edge at the top of your object, put the other top part of your straight edge right at the very center of the lens, and that passes through the lens undeflected. Now, if you've been careful with your and kept your distances straight and measured your kept your lines straight and measured your distances, then all 3 of those rays will converge at the same point. And you can see I got pretty close. Mine don't all 3 converge at exactly the same point, so my lines weren't perfectly straight. But you can tell that my image is going to be right here. Now, let's see how our ray diagram compares to what we found algebraically. First of all 3 of those rays truly do converge at that point. And if the rays truly do converge there, then we call the image real. That matches what we got with our ray diagram. Okay. Or that matches what we got algebraically. Second, we see that we got an image that is a little further away from the lens than the focal point. And that also matches what we got algebraically. We got that the image location algebraically was 3.3 centimeters away from the lens. The focal point's 2 centimeters away from the lens, so that appears to match up. Finally, we got that the image is smaller than the original object. That's what we predicted with the magnification of 0.6 or 60%. And in the ray diagram, the image is upside down or inverted. We predicted that algebraically because we had a negative magnification. Okay, so that is how you draw the ray diagram and solve algebraically to find the image location for a converging lens if the object distance is greater than the focal length. All right, now let's do the second case. That would be the case in which the object distance is less than the focal length, or in other words, the object is placed between the focal point and the lens itself. So we'll stick with a lens that has a focal length of 2 centimeters, but this time we will say that the object distance is only 1.5 centimeters. Okay, so we'll say DO is only 1.5 centimeters, or 3/2 centimeter. In other words, less than 2. Okay, we still use the same lens equation. 1 over f equals 1 over the object distance plus 1 over the image distance. So we have 1 over 2 centimeters equals 1 over 3/2 centimeters plus 1 over di. We'll subtract 1 over 3/2 from both sides. So you have 1/2 minus 1 over 3/2, or 1/2 minus 2/3 equals 1 over di. We need to find a common denominator. That would be 6. So 1/2 becomes 3/6. And 2/3 becomes 4/6. Right, so we have 3/6 minus 4/6. That's minus 1/6. 1 over di is minus 1 over 6. So di is equal to minus 6 centimeters. The fact that we have a negative image distance means that our image will be virtual. As for the magnification, we have m equals minus di. Di is minus 6. Do was 1.5. Okay, so we have a magnification of 6 over 1.5, which is 4. Those two negatives cancel. Okay, so we end up with a positive 4 magnification. The positive on the magnification means that our image is going to be right side up, or upright, and it will be 4 times bigger than the original object. Okay, let's see, how would we do this with a ray diagram? Okay, once again, I have already drawn the lens and the principal axis, marked the focal points. The focal points are 2 centimeters away from the lens. So I also need to put an object that is 1.5 centimeters away from the lens. So that will be about right here. Okay. Now we'll use the same 3 principal rays that we used before. Principal ray number 1 is parallel to the principal axis. So you put 1 point of your straight edge at the top of your object, and make sure that your straight edge is parallel to the principal axis. Okay. So here is, and when it gets to the center of the lens, move your straight edge so that it passes from the center of the lens through the focal point over on the other side of the lens. There we have it. Okay. All right, then the second principal ray. Through the focal point, rays that pass through the focal point will emerge on the other side parallel to the principal axis. Okay, so you should put your straight edge so that it passes through both the focal point and over the top of your object, like this. Okay, now if it doesn't hit your lens, that's okay. What you can do is you can extend an imaginary line through the center of your lens. You can extend that imaginary line up as far as you need to, so that when this ray hits that line that would be the center of the lens, then that should emerge parallel. Oh, I didn't change color. Let's go back to red. There we are. Okay. I'm going to get rid of some of this algebra because it's getting in the way of our picture. And then finally, the third principal ray is a ray through the center of the lens, will be undeflected. So put part of your straight edge at the top of your object, the other part of it through the exact center of the lens. There we go. All right, now what you will find, what we see is that these 3 rays, if I look at the red, green, and blue rays, they are never going to actually intersect anywhere over there on the right because they're diverging from one another. They're getting further apart the further away from the lens they get. So they're never going to converge for real, meaning that the image is not real, it's virtual. And that agrees with what we determined algebraically. So in that case, what you do is you extend the rays backwards from the lens. So let's extend the blue one backwards. I'll extend it with a dashed line. Okay, I've already extended the green one backwards. Let's extend that red one backwards. And we see that although those three rays never truly converge over there on the right, to an observer that was on the right looking over to the left, it would appear that those three rays are all coming from right there. So that means our image is going to be a virtual one, and it will be like this. Okay. So let's see, how does the magnification and location compare to what we predicted algebraically? First of all, we predicted algebraically that it would be about 6 centimeters away from the lens, which is 3 times further away than the focal length. So it is further away from the lens than the focal length, maybe 2 or 3 times further away. Also, we predicted that because we had a positive magnification, that the image would be upright, and in fact it is upright. It has the same orientation as the original object does. And we predicted that the image would be 4 times bigger than the original object, and definitely in our picture it is quite a bit bigger than the original. So our ray diagram and our algebraic method agree with one another. Anytime you have a converging lens, you're only going to have one of those 2 cases. If, like this, the one that I just worked, if the object is between the focal point and the lens, you're going to end up with an upright virtual image. If, on the other hand, like we had in case 1, if the object distance is greater than the focal point, you will end up with a real image, but it will be inverted.